Today I'm just going to be very briefly introducing the concept of electric potential. Tomorrow we'll actually get into the calculations of potential and a bunch of different configurations, but today we're just going to look at the concept. So electric potential energy is super easy to understand if you use gravitational potential energy as kind of a basis on how to think about it conceptually. So you should remember about gravitational potential energy from AP Physics 1. And we calculate gravitational potential energy. U is for potential energy. Don't know if you guys have used that variable before, but that's the standard variable for potential energy is U. So U gravitational equals mg times h. And basically all gravitational potential energy says is that if you raise an object, it gains potential energy because if it fell from there, it would get more kinetic energy than if it fell from somewhere lower. So like if we look at that in conjunction with this sphere, which we're going to assume is the Earth, if you take an object that's right here on the surface and you move it up that much, that h, it's going to gain a lot of potential energy. And that energy is just due to its position, because if there's something right here being held and it falls, it's going to gain a lot of kinetic energy. So its position gives it the potential to have kinetic energy. So gravitational potential energy is very similar to electric potential energy. And there's actually quite a few similarities between electrical force and gravitational force, which leads to similar ideas about fields and potential energy. So if you look at the universal law of gravitation, not just gravitation on Earth, the universal law of gravitation says that the force of gravity equals gravitational constant g times the mass of a thing times the mass of another thing over r squared, which looks strikingly similar to Coulomb's law for electrical forces, which is K, or 1 over 4 pi epsilon naught, Q1, Q2 over r squared. And that's because they are both field forces, and each force is proportional to the inverse of the square. And that's why they're both called inverse square laws. And the way we generate gravitational potential energy is we move something in the opposite direction of that force. So the force of gravity is pulling towards the center of the Earth. If we take an object and move it away from the center of the Earth, outwards, we give it potential energy, because if we let it move again, it's going to fall back towards the Earth. Electric potential energy works pretty much the same way. Like if you consider a point charge that is negative and a positive test charge, we'll start with it right here. The negative charge is going to pull on the positive charge. So if we move that charge away, we're going to give it some potential energy because our point charge is going to try to pull it back. So that's one way to generate electric potential energy. However, because the electric force can be either attractive or repulsive depending on the charges of the objects involved, it's slightly more complicated. So another example might be we would have a positive point charge and a positive test charge. So my positive charge is going to be pushing away on the positive test charge. Now if we scoot that test charge closer, we have now given it some potential energy, but kind of seemingly in the opposite direction. So while gravitational potential energy is a really good stepping stone for figuring out electric potential energy, they do have some differences that have to be considered. Now, the way we calculate potential energy is using the concept of work, which hopefully you learned back in AP1. And the relationship between work and potential energy looks like this. It says that work is the change in potential energy, and it also equals force times distance. And a little caveat to this is that work is equal to the total change in energy, but here we're not going to be considering kinetic energy just yet. And the consequence of this equation, of this law, is that we can determine the electric potential energy of a charge by calculating how much work it took to move the charge there. So, for example, in gravitational potential energy, if you've got some object at height 0, and you need to calculate its potential energy at a height of, say, 10, you use the force, not the Star Wars force, the force of gravity, mg, and you multiply it by the distance that you move the object, which is mgh. So that's your potential energy there. However, this is a bit of a simplification because we're using a constant g, which is the acceleration due to gravity, g equals 9.806. And we're assuming that over those 10 meters that g is constant, it's not changing, and we can usually assume that just fine because we are, miles away, many, many miles away from the Earth's center, so a 10-meter gap isn't going to change the gravitational pull that much. However, with electrical charges, we are going to be working at distances where the radius will drastically change the force due to Coulomb's law. So we can't do anything quite as simple as mgh for calculating the potential energy due to a point charge. Now, when you get to calculus-based physics, you'll learn that you can actually do the integral of the force dr, which is a way of kind of summing up force times distance for a variable force where the force is changing constantly according to some function, which it does due to Coulomb's law for electric forces. We can't consider the electrical force to be constant in the situations we're working with. Now, the concept we were just working with is electric potential energy, and it is an important concept, but it is not the most important concept of this chapter. The most important concept is electric potential, and they seem really similar. I mean, there's only one word difference: electric potential energy versus electric potential. And here's the difference. The potential energy is referring to a specific charge's potential energy in space. I'm going to make this slide smaller so I can write. So, for example, if we have a charge, a positive point charge that's generating an electric field points away from it because that's convention for positive charges. All right, and we've got a small particle Q right here. Now, the potential energy of that particle is based on the force required to get it there. And we know force is K Q1 Q2 over R squared, which is dependent on the charge of whatever charge we're looking at. It does depend on that. Just like when you're calculating potential energy from gravity, you have mass as a term. The mass of the object matters. And that is for potential energy. However, electric potential is looking more at the way the electric field is at that point, and is not dependent on the test charge. Let's see, I'm going to erase this little Q. Okay, so potential energy is for the specific charge, but electric potential is looking at the field at a point. So we would say at this point, we're going to look at the potential that's generated by the field. So if we stuck a particle there, it would have potential energy. And really, mathematically, all it is taking that potential energy and dividing it by Q, so that the Q is irrelevant, just like we did with the difference between electric force and electric field. So electric potential is a scalar field that will tell you the ratio of potential energy to charge at any point. So it is not dependent on a charge being there. It is a quality of the field. And the way the textbook words this is that it is the potential for potential energy. So it's saying if we stuck a charge here, it would have some potential energy. And if you want to look at the gravity analogy again, this would be like saying if you've got some area of land at some elevation, so this was going to be my zero line. At every height h, so we'll call this like 6 meters for funsies. If you ignore the mass, there would be a potential of gravitational constant times the height. So 6g times the mass at any point on this line. So you could have in a gravitational field a gravitational potential that is g times h. So whenever you put some mass there, it will have the potential energy mgh. So you're just taking out the specific object's qualities and you're looking only at the qualities of the field. And that really is its similarity to electric field. The electric field shows how source charges would exert a force on Q. So we know that field was force to charge ratio, and from that we got that the force on a charge is the field times Q. Similarly, electric potential is going to tell us how a field provides Q with potential energy. So electric potential is a field. It tells us at every point in space how the source charge would provide some arbitrary charge with potential energy. But a difference between electric field and electric potential is the type of field. So an electric field, say generated by a positive charge, had magnitude and direction. It was a vector field because it was talking about and describing the forces on particles. But electric potential doesn't have any direction. It's just a numerical value at each point in space. So if you think about our gravitational example, at each point in space, it was just gravity times height, which is simply a number. It is not a vector. It is a scalar field. It just tells you at every point the potential energy, because energy is not a vector, it is a scalar. So we can use the idea of electric field to think about it, but it is a different thing and a different type of field. And really, that's all I have to talk to you about today for electric potential. We'll talk about how to calculate it tomorrow and get into all of the nitty-gritty gross details. Thanks for listening. Have a good day.